Swayam Prabha. Digital India. Educated India.
Okay, good afternoon and welcome back. So before in the previous class, what we saw was a very quick and rushed introduction to linear algebra, vectors, matrices, determinants. Also looked at a very concise understanding of when solutions exist, when they are unique, and so on. And then we went on to giving some more geometric properties to vectors. We are able to define lengths of vectors, we are able to calculate angles between vectors and come up with when vectors can be called to be perpendicular to each other. That happens when the dot product of these two vectors is 0, then the vectors are called perpendicular. We also saw another way of factorizing matrices, which is a QR factorization. Apart from the LU decomposition, which is used for linear equations, QR replaces the columns of A as, instead of arbitrary columns which could be arbitrarily oriented, they replaced, those columns are replaced by perpendicular columns, each of which has unit length. Okay, so now what we are going to see is a very quick introduction to how orthogonality is useful. This is least squares, and of course, it will be covered in much more statistical detail and by colleagues who will do the statistics part than learning and machine learning and model building by other faculty members. I will just bring out very quickly what is the geometric and the interpretation of some of these problems. So why we are solving this and in what sense it is meaningful. This is for instance, I use the word best estimate. Right? I'm just put it deliberately. I put it in quotes, and others will expound more about these. But I'm going to treat this purely as a geometry problem. So now we have all of us are rather health conscious, so we take our readings. We step on a bathroom scale and step out of it, and we take, say, maybe n of these readings, and they're likely to be, it's very unlikely that you will get the same weight reading each time. So we record them, and we have n of these, W1 all the way up to Wn. It's very unlikely that they are all the same, so there will be slight discrepancies and deviations each time you step on the scale, and we're going to assume that the true weight has not changed. I mean, the interval is so short enough that the time when we have taken all these readings, the true weight of our true weight has not changed. So now I'm going to collect all of it as a vector. All the weights, I put it as a column vector of size n cross 1. Now let's assume the true weight is W. So corresponding to the n observations, the true weight also, there is a true vector of true weight, which is a single weight does not change. So the single weight W times this vector over here. So now the true weight is unknown. All you can do is get an estimate of the true weight over here. The true weight, whatever you call it, W is unknown, so you can only get an estimate of that, W star. So let me call that estimate as again a vector, W star all the way over here. Now the question is, what is the best possible estimate of this, of W star? So intuitively we know it is the arithmetic mean. Right? And now we will also see, I'll come up with a geometric problem in terms of vectors and show how this can also be derived from that under certain conditions. So why this best, why did we choose this notion of best? Because I'm going to measure distances and so on, and why did we choose this measure of distance and so on is not something which I will cover, but I'll just keep it as linear algebraic as possible. So now we have two vectors over here. The vector of observations that we have, as I said, this is only a cartoon picture, it doesn't make sense because there are several, it's not a two-dimensional vector, and this is my vector of the true or the estimate of those weights. Now if of all the weights that I measured were equal to each other, then these two vectors would be collinear. However, even if one of the weight is slightly different from the others, this vector is not going to be collinear, because remember, in this vector over here, the base vector that I have, all the components are equal. So let me also so this is equal to W star into what is called the vector of ones. If at least one of the recorded weights is different from the other, then this vector will not be collinear with this vector, because along this vector you take any scalar multiple. Remember, this is just a scalar multiple of the vector of ones, so any time you multiply, all the points along this line have the same components. So now the question is, I have this recorded vector, I want to get an estimate of my W star, which is a true estimate of the truth, from using this. And these two vectors are not collinear with each other. So what is the notion of best? One geometric notion is I try to minimize the distance between this vector and all the vectors over here. Right? And when is this distance minimized? When is the distance between 2 points minimized? What is the shortest distance between two lines? It is a perpendicular distance. Right? So I can go anywhere along this line, but I want to minimize this and I want to minimize the distance of this line from this point over here, because this point is fixed, my known observation. I can go anywhere along this line, and I want to find the shortest distance between a point on this line and this point, and that shortest distance happens when this is perpendicular. This is what I call the error. Let me call this the error vector, or just a vector over here. It's an error or a residual vector, or just for, it's typical to call it by E or R, or error or residual vector. So I can go anywhere along this line, and I want to find the shortest distance of this line from this point, and that happens when this is perpendicular to this line. So let me call this W star over here. This point is W star over here. So if I want to, I don't know what is W star. I want to find out W star such that W star is as close as possible. W star times 1 is as close as possible to this vector. That's the geometric interpretation that I am going to give. And why should I use this notion of best? Remember, I said this is a so-called best estimate of W star. Why did I say that this distance should be minimized? That is something which we will not do, but we will treat it as a pure geometry problem. Let's not get into why this is a meaningful notion of distance and so on. It's just a pure geometry problem which all of us can appreciate. I want to find this W star such that it is as close as possible to this point over here. And we know that will happen when this so-called error vector is perpendicular to W star times 1. So E is equal to, let me call this W1, W2, Wn minus W star times 1, 1, 1, dot, 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 1. Now I have said that this should be perpendicular to, right? The error vector should be perpendicular to the 1 vector, so vector of 1s. So what does it mean when two vectors are perpendicular? The dot product is 0. So let me say 1, 1, 1 times W1 minus W star, W2 minus W star, this is equal to 0. Remember, W star is unknown, all the other Wi's are known. So you just expand this out, what will you get? W1 plus W2 all the way up till Wn minus n times W star equal to 0. W star is equal to sigma Wi by n. So the arithmetic mean. So even though we have been, if you give me 2 or 3 observations in a lab course, we have always been trained to take the arithmetic mean. What we really solved is a geometry problem. We are trying to find, if you are trying to estimate a single constant, like in this case my single constant I'm trying to estimate is the true weight over here, and I take the arithmetic mean of these observations. What I have really done is a least squares problem. I am trying to find, or rather, actually I won't say least squares problem, I am trying to find a shortest distance problem, because I try to find the shortest distance of this point from this ray over here. Okay, so now likewise, this is I introduced this problem in the starting of this class. So I have some observations over here, and I want to find out, and I expect that this has a linear relationship. So this is x and y equal to mx plus c. I expect there is some kind of a linear relationship between them. So there are two unknowns, this intercept c and the slope m. And there are several observations. Let me call this x1 comma y1, this is x2 comma y2, and so on, and this is xn comma yn. So let me write down what kind of linear relationship I expect it to satisfy. So it would be y1 equal to mx1 plus c, y2 equal to mx2 plus c, ym equal to mxn plus c. So let me take all of this and write it, let me take all the y's and put it down in one vector on the right hand side as y1, y2, all the way up till yn. And the left hand side also, there are two unknowns over here. So I'm going to write this as mc x1, x2, all the way up till 1. So if you can expand this out, this is what it makes sense. You can see this is a. So now again you can think about this as I am trying to find combinations of these two vectors. The first vector is this plus a combination of this vector such that this is equal to my vector of observations. We have to now change your thinking slightly. I am now going away from the xy plane into another plane, another vector space where there is one vector is a vector of my x's, one vector is a vector of 1's, and my right hand side vector is my vector of observations. By the same logic, what I am going to now do is I am going to try to find 1's, so this I will going to call my vector as A, and maybe this as theta and this as B. Right, I have now more columns, more equations and unknowns. If all my data points were correct, all my observations were correct, then they would all be consistent. They would all be satisfying the same straight line equation, and all of them would be lying on the same point. That is, I can find my right hand side vector y1, y2 all the way up till yn such that it could be written as a linear combination of the columns of A. If everything were perfect, if there were no error at all, just as in the previous case, if there were absolutely everything, I had a very, everything were perfect, all my observations of weight would be exactly equal, and that would be lying exactly on my parallel to the vector of 1's. Here again, if everything were perfect, my vector of observations of y would be exactly, could be represented as linear combination of the columns of A over here. However, it's not going to be the case that it can be done, because as you can see over here, the points are not all lying on the same straight line. So this representation is slightly different from the geometric picture over here is different from this. The geometric picture over here is there is one this is one column A1 and this is A2. So I have here A1, I have here A2, and B is over here. This is my B. I am trying to find linear combination of these columns such that they could be written as B. However, when B cannot be written as linear combinations of these, that is B cannot be written as a combination of columns of this, then it is going to stick out. Then again I can ask the same question. What combination should I choose of A1 and A2 in the best sense? So the geometry problem that I will be asking is A2 vectors over here, A1 and A2, they define what's called a subspace. So I can find the vector B is not lying in the subspace, in the space spanned by these two vectors. So I'm trying to find, if I can shade this, if I take all possible linear combinations of A1 and A2, I'm going to get, like a plane, I'm going to get a subspace formed by all possible combinations of A1 and A2. Unfortunately, B could not be written exactly as a combination of these, so B is going to stick out. So again I can ask a similar geometry problem. What is my best choice of A1 and A2? My best choice of A1 and A2, suppose it is some choice, something like this. It is some choice of A1 and A2 with some M star and some C star. It is going to be such that this is perpendicular. The difference between this, the so-called the error vector, that is perpendicular to this plane over here. If it is perpendicular to this plane, it is perpendicular to every vector in that plane. And when I say plane, I will talk of subspace. It is perpendicular, just think of, it is perpendicular to the so-called plane spanned by these two vectors over here. If this error vector has to be perpendicular to every vector in this plane, it has to be perpendicular definitely to A1 and A2. It has to be perpendicular to both A1 and A2. So what does that mean? So let me call this A1 M plus A2C is equal to B, right? My constants are C and M. Now my error vector is what? Y minus A1M minus A2C. Now that combination M and C are unknowns. I'm going to choose that combination such that this point is as close as possible to my observed vector B. Because if I take all possible choices for M and C, I will get different points in this plane. I want my point that I got by these combinations, I want it to be as close as possible to my observed vector B. And why do I want it to be as close as possible? Again, that's I will not delve upon that, but it's like treated purely as a geometry problem. I'm trying to find I've given this point over here, and I'm given this plane which is formed by all possible combinations of the vectors a1 and a2. I'm trying to find the shortest or the closest point of this point from this plane. And geometrically, when is this going to be the shortest point distance? When the error vector is perpendicular to this plane over here. So the error vector has to be perpendicular to this plane. If the error vector is perpendicular to the plane, it is perpendicular to a1. Error vector is perpendicular to a2. Right? Now, how is this useful? So I can write a1 transpose error should be equal to 0. Likewise, I can write a2 transpose error is equal to 0. So what do I get? What is error? I can take this and then write it as a1 transpose a2 transpose E is equal to 0. I can do this because I am just concatenating the rows together as a matrix. And what is this matrix? A transpose. Because A1 and A2 are forming the columns of A. So A1 transpose and A2 transpose, if I write it in a horizontal manner, I get the transpose of the matrix A transpose. And what is E? E is Y minus A1M minus A2. Or okay, maybe I should have just, I'll do this. So I'll wipe this out over here. No, sorry, I'll just go back to. So let me just A1 transpose Y minus A1M minus A2C equal to 0, and then I get A2 transpose Y minus A1M minus A2C equal to 0. Now what happens? You have two equations and two variables because M and C are your unknowns over here. And you have two equations and two variables which you can solve. In the previous case, when you wrote it as a standard problem, there were many equations and two variables. However, they were not consistent because your B vector was not lying in the space formed in the subspace spanned by the columns A1 and A2. Therefore, you are forced to do we said we will work with the in the plane formed by the vectors A1 and A2. We will find the closest point to the vector B over here, or vector, in this case I call it the vector Y. So I have two equations, two unknowns, and I can solve these. In the previous case of this estimating a single constant, it was just the arithmetic mean. In this case, if you recall your you may have done this in statistics courses also. There are these, you would have seen these in terms of variances of x and y, and there is a standard formula which is available for M and C. This is no different from that, but except this is just purely treated as a geometry problem. I am trying to find the shortest distance of the point y or b from this plane spanned by the columns A1 and A2. So what happens in the larger case, in an arbitrary case? When we discussed linear equations, I said we will look at the square case. Now I am going to look at what's called the overdetermined case. A is m cross n, x is n cross 1, b is m cross 1, and m is larger than or equal to n. There are more equations than unknowns. In the square case, there are as many equations as there are unknowns, and the solution, nature of the solution dependent only on the determinant of the matrix and whether B could be written as a combination of the columns. Here there are more equations than unknowns. So if these were, maybe this is the first column, this is the second column, and so on. There are several columns of the matrix A, and you have a vector B which you are trying to write as a linear combination of the columns of A. Unfortunately, these equations are not consistent. That is, the vector B cannot be written exactly as a linear combination of columns of A. So what do? The columns of A span a certain so-called subspace. It's not a plane, but it's a different. You can think of it like because I can only draw certain things in two dimensions. I've drawn it to represent a plane, But again, the same intuition holds good. I'm trying to if I take combination of columns of A, I'm going to remain in this subspace. I'm going to get a point over here. I'm trying to find a point or a vector which is formed by the combination of columns such that it is as close as possible to this vector B. So I'm going to try to find x1 a1 plus x2 a2 all the way up till xn an. There are n columns, and I want it to be as close as possible. I want to choose my x's such that this is as close as possible to B. So I want to choose my constant, my unknown, yet to be determined coefficients x1, x2, xn, an, such that it is as close as possible to the vector B. Again, I use the same idea of when will this happen? When I drop this perpendicular. The shortest distance when this point is closest when this is perpendicular. So again, I will define my E, or the error or the residual vector, as Ax minus B. Now Ax minus B, my x is chosen such that it is shortest when error is perpendicular to A1. Right. So I will write this as A1 transpose Ax minus B equal to 0. And there are n columns, so I am going to get n such equations. So for each of the column I get one equation, there are n equations. Now I get n linear, each of this is a single equation because this is a scalar over here. The right hand side is a scalar, the left hand side after multiplication is a scalar. So what I am going to now do is, I am going to assemble everything into one single equation over here. I will just concatenate all of these and then write it as this is my, because Ax is going to remain over here, B is over here. So Ax minus B has to be perpendicular to every column of A. And when I write it down and concatenate everything, I get A transpose into Ax minus B equal to 0. What do I get over here? A transpose Ax is equal to A transpose B. And what are the sizes of this equation? Remember, we started with more number of equations and variables. So here if you look at it, the size of A transpose A is n cross m, this is m cross n, this is n cross 1, again this is going to be n cross m and m cross 1. So finally I get a square system of equations of size n cross n. Now when the columns of A are independent, we will not prove this, when the columns of A are independent, this matrix is invertible. A transpose A is invertible when the columns of A are independent. Determinant of A transpose A is not 0. Therefore, I can solve this as A transpose A inverse A transpose B. So this is called the normal equation or the least square solution to a system of overdetermined equations. Overdetermined meaning there are more equations than unknowns. Unfortunately, they are not consistent. If they are consistent, you will get the correct solution. I mean, there's only one solution. If they're consistent, you'll get the correct solution. If they're inconsistent, there is no solution. You can only get the so-called best solution. The best solution is obtained by finding those combination of columns of A such that the error between this so-called this vector over here is perpendicular to the columns of A. And you end up getting a square system of equations because A transpose A is now a square matrix. It is invertible if the columns of A are independent. So this is the so-called least squares. This is also studied under the least squares idea. This is very standard regression. It will come in regression. It will come in machine learning, model building, and so on. And those colleagues of ours will be giving you other interpretations of why did we choose this notion of distance. There are several ways I told you could measure distance. This is only one of the ways in which you can measure distance. Why did we choose this notion of distance? So on will be clarified by them. But at least think of this purely as a geometry or a linear algebraic problem. We are trying to find combinations of columns of A which are as close as possible to my observed vector B. So just to recap, when you have more number of equations and variables, it's likely that the right hand side is vector is not possible to be expressed as a linear combination of the columns of A, or the equation is not consistent, then we can only search for the so-called best solution. And one notion of best is to minimize the distance, of the observed vector B from the subspace spanned by the columns of A. And that happens when there's a certain perpendicularity condition can be written, and you will end up getting as many equations as variables, and this can be solved if the columns of A are linearly independent.